So here it says describe a preparation for magnesium hydroxide, which is MgOH2, and predict its solubility. Milk of magnesia contains mostly magnesium hydroxide and is effective in treating acid reflux. Calculate the volume of a 0.035 molar HCl solution needed to react with 2 spoonfuls of milk of magnesia. So that's part B. So part A, describe a preparation for magnesium hydroxide and predict its solubility. We didn't really talk about the solubility rules and how to predict whether something's soluble or not. So I'm probably not going to ask you to do that. If you look at the information given later in the problem, it says that 0.08 grams of MgOH2 per milliliter. That's a relationship it gives you. So part A here is really general. It doesn't say how much they want us to prepare. It just says describe a preparation. So if you wanted to prepare 100 milliliters, and you want to know how many grams of MgOH2 to put in, well, you take that 100 milliliters and use this relationship. Anyway, the preparation is going to depend completely on when you make that mixture, how much of the 2 components of the mixture there should be relative to one another. So if this is the relative amounts, then I just need 0.080 grams per milliliter. And so then the milliliters cancel. If I want to make 100 milliliters, it would be 8.0 grams. So I would just measure on the balance 8 grams of MgOH2. Maybe put that in a mortar and pestle, grind it up real good. Pour it into 100 milliliters of water, mix it up, and I've got it. So that's pretty straightforward. The reason it's called milk of magnesia is because it's cloudy, and that's because MgOH2 is not very soluble in water. It's a pretty strong attraction between the Mg2 plus and the OH minus. So in water, they don't really fully separate. They will separate to some extent, but not fully. Even if they don't separate though, even if I had an MgOH2 solid, if I react an acid with that, it can still react because I still have OH minus on the surface of that solid, and when an H plus from an acid comes in contact with that, the OH minus is going to pick up that H plus and become water. And then that will move into solution, and it will expose the next layer of OH minus on the next layer of the solid, and then that will react layer by layer until the solid is gone if I keep adding acid to it. So if you look at part B, it says we want to know how much HCl is needed to react 10 milliliters of milk of magnesia. So how many milliliters of HCl do I need to react 10 milliliters of the MgOH2 solution? It's not really a solution because it's not fully dissolved. So I'll say suspension because the solid is suspended in the water, not really totally dissolved in it because the ions are not fully separated. The calculation here isn't affected by the fact that the MgOH2 doesn't fully dissolve, because an acid-base reaction can happen between a liquid and a solid. It doesn't require everything to be dissolved first, because even the solid is still reactive on its surface, and it just takes longer because it has to react away the surface one layer at a time, rather than allowing everything to be in solution ready to already be colliding. So it might take longer, but the question doesn't ask us anything about how long it will take. It just says, how much HCl will it take to fully neutralize the base? So if you have an upset stomach and you've got too much HCl in there, you've got a little acid reflux, and you take 2 spoonfuls of milk of magnesia, which has MgOH2, it's the OH minus that neutralizes the HCl that's causing you discomfort. And so we just basically want to calculate, if you do take 2 spoonfuls of milk of magnesia, how much HCl can that really neutralize? Right? So that's what we're interested in. And the concentration of HCl in your esophagus, where the milk of magnesia is going to help reduce that acid reflux, might be around 0.035 molarity. So that's got to be given. And that's a relationship. Right? A lot of people on the last exam just treated this molarity as molarity, and if you don't recognize that as a relationship, it's going to really make it impossible for you to do any calculations with it, because that's the whole point. It's a relationship. It's not molarity per liter. Molarity is molarity, and that is moles of a substance per liter of solution. So make sure you understand that, and you can separate that out as a relationship. That's going to be an important relationship here, because if we have information about one substance and we want information about a different substance, we've got to get to moles first, and we have to have also a balanced reaction. So we need a balanced reaction here between the HCl and the MgOH2. I need that because if I convert this into moles, and I want to convert to HCl, I need the moles of HCl to moles of MgOH2 relationship. And so that, as an acid-base reaction, we can predict the products. The acid's going to lose an H+. The OH minus is going to accept that H+. I'm going to make water. And then the Cl minus will be free, and the magnesium will be free. And those are just spectator ions. They're not involved in any way, really, in any significant way, just to keep the charge balanced. So then I've got to balance that reaction. So I'll need 2 of these, 2 of these, and 2 of these. So if I've got 10 milliliters of this, I need to convert that to moles, so I can use this 2-to-1 mole ratio to figure out how much HCl, and then I use this relationship to figure out the volume of HCl. So I'm going to need more space here. I'm going to probably need 2 lines. So I'll start again here. This is part B. I want to know how many milliliters of HCl is it going to take to neutralize 10 milliliters of the MgOH2 suspension. So then the book gives us a relationship for this question. It says there's about 0.080 grams per milliliter of suspension. So that's a relationship. For every 1 milliliter of suspension, 0.080 grams of MgOH2. I'm trying to convert to moles. Why do I want to convert from milliliters to grams? Because once I have grams, I can use the masses on the periodic table to get moles. So I would get my calculator, and I would take 1 magnesium, which is 24.305, plus 2 oxygens, plus 2 hydrogens. It's 58.32 grams of MgOH2 per 1 mole. Now I've got moles. The whole point of that was to use this relationship. So I can say for every 1 mole of MgOH2, that requires 2 moles of HCl. So I'll just continue this on the next line. Now, I've got a lot of stuff canceled out. I've got milliliters of suspension, grams of magnesium hydroxide, moles of magnesium hydroxide. I've got moles of HCl. I want milliliters. So I use the molarity. So I want to cancel the moles now. So I put the 0.035 moles of HCl on the bottom. That's equal to 1 liter of HCl solution. And I'm interested in milliliters, so I would do a liter is 10 to the third milliliters. Cancel the moles and cancel the liters. So I've got milliliters now of HCl solution, which is what I wanted to know. So when I put that in my calculator, two spoonfuls of milk of magnesia could neutralize 784 milliliters of HCl solution. That's a lot. Instant relief. So I'm not really worried about sig figs here because they didn't say, they just said we have about 10 milliliters. 2 spoonfuls is about 10 milliliters. So, that's really approximate. So, if I report my answer this way, it's implying 3 sig figs. But, honestly, I really only have 1 sig fig here. On an exam, I'd be very unlikely to only give you 1 sig fig, but if you did have 1 sig fig, to correctly report it that way, it'd be 8 times 10 to the second milliliters of the solution. So about 800 milliliters.